Video is going to be the lecture notes that goes with chapter 6 about the normal model. This is actually the last chapter for our first unit. So once we finish going through the material for chapter 6, we'll begin reviewing before our first test. Okay. Now, this chapter is probably one of the longest chapters for the entire unit, and there's a lot going on. And what's really fun about this chapter is if you were to ask other adults who have taken statistics in their educational career, they would probably mention doing this work as one of the most memorable experiences of statistics. So we're going to first talk a little bit about using standard deviation to help us standardize data values into something called z-scores, and then move further into the most important topic of this chapter, which is the normal model, your first experience using a model. Okay, so let's start by talking about this standard deviation. If you remember from chapter 4, standard deviation is basically a measure of how far away your data values are from the mean, and it finds that average distance. So if it's a small standard deviation, close to 0, then your data values are fairly compact or close to the mean. If your standard deviation is much larger, then there's going to be more variation or more spread in your data values. Okay, so what you have here, this formula, is the formula that we're going to use for when we're finding z-scores. Okay, so this is saying the z-score is equal to y, which is our data value, okay, minus y bar, which is another way to describe the sample mean, right, or the average from your sample, and then divided by your s, which is the sample standard deviation. Okay, we'll see later on in this video another way to use this formula with different symbols, but for now, this formula is coming from a sample. Okay, now, the whole idea of doing this, of standardizing, is that we can now compare things that don't have the same units. Okay, so that's one of the main benefits. All right, and you'll see that when we do this in practice, standardized values have no units. All right, so whenever you standardize something, you say your z-score is 2, you're saying that data value is 2 standard deviations above the mean. If you have a negative z-score, like negative 1.6, then you're saying that data value is 1.6 standard deviations below the average. So you will be having positive and negative ones here. Now, what they're basically doing when they standardize is we're first shifting the data. So we'll do I think in the video another video that I'll post with some examples or exercises, you'll see some of this. But basically, when you shift data, that means you take a number, whatever it is, some constant, and you add that number or subtract, depending on what you're doing. And you take that number and you add or subtract that constant value to each data value in your data set. And what that's going to do is that's going to take your measures of center, like mean, median, and mode, and it's going to change them by that same constant amount. Now, the interesting thing about shifting data, if you just add or subtract a constant amount to all of your data values in your set, then your measures of spread will be unchanged. All right, so this visual here is just showing you that when they shift the weight for men from kilograms above the recommended weight from just kilograms, right? So they're shifting the data. You'll see actually there's no change in the shape of the histograms, right? Or the box plots. So when you shift the data by adding or subtracting a constant amount to each value, you're not actually going to change the shape of it. Now, let's talk about rescaling data. Now, this is another part in the standardized formula. The rescaling is the division part, right? But if you use multiplication, that's the same thing, rescaling. So if you divide or multiply all of your data values by a constant value, not only are the measures of center going to change, like mean, median, and mode, right? Those are going to change as well. But measures of spread will also be changed by that constant, okay? So you can see that in these histograms, where they've changed from weights in kilograms to weights in pounds, they're using multiplication. And so that's going to end up changing the shape of the histogram. Now, a couple more things about z-scores. All right. The reason that we talked about that rescaling that shifting and then rescaling is because that's what you're doing in your standardization formula, right? When you do y minus y bar, that means you're taking your data value and you're shifting it by subtracting the mean, and then you're dividing by the standard deviation, which is your rescaling. So that's why this happens in this chapter. All right. So if you were to standardize, all of your data values and make a histogram with those z-scores, you're not actually going to change the shape of the distribution. It will look the same as the original histogram. All right. If you do that, though, all that does is it takes your center or your mean and it makes it 0 as opposed to whatever it was for your data set. And your standard deviation, instead of whatever number you had, it changes it to 1. All right. So you'll see when we do this normal model coming up that we're going to have mu and sigma, which are the Greek letters for mean and standard deviation. And so when you standardize, you have a mean of 0 and a standard deviation of 1. All right, let's keep going. All right, so here's that normal model that I just mentioned. All right, this model is probably the most important model in statistics, and it occurs the most. All right, you've seen it probably in as a bell-shaped curve. That is the normal model. Key thing is it's only appropriate if you have a distribution that is unimodal and roughly symmetric. So if we're looking at a histogram and it's showing any type of skewness or multi-modes, right, we're not going to use the normal model, not appropriate. I already mentioned that we're going to be using this way to write normal models, right? The reason that we use the symbols mu and sigma, those Greek letters, is because these are technically not summaries from our statistics, okay? They don't actually come from the data, all right? So we call these parameters, all right? And because we call them parameters and they're not actually from our data set, when we write the formula compared to what you guys saw before is instead of using this formula, which we saw earlier on in the slides, right? Y minus Y bar over S, right? We're going to use this formula for the model, all right, which has mu and sigma. So the work that we'll do will be the same, but I'm going to make sure you guys understand that when it's appropriate to use the symbols for the model, for working with a model, and if we're not working with a model, if we're working with real data, then we'll use the Y bar and the S. Okay, so if you have summaries that come from the data, those are called statistics. Okay, so you'll see later on when we get further in these units, I always like to think of alliteration to help me here. We have something called sample statistics. So your statistics from the sample and population parameters coming from the population. That'll make more sense in later chapters. Now, this is something that we kind of start talking about in the first semester because it's so important in the second semester when we get to hypothesis testing. But this nearly normal condition is basically just to take a moment before you use the normal model is like, do we feel okay assuming that our distribution is unimodal and roughly symmetric? Because if it's not, if the distribution of your data values of your data set is not unimodal and roughly symmetric, you should not be using the normal model. So basically, we'll just look at the histogram and see if we think the shape is unimodal and roughly symmetric. All right, one more thing that's interesting about the normal model before we finish up. All right, so this is called the 68, 95, 99.7 rule. And basically, we'll be talking about this a lot, but if you are using a normal model, then what you're saying is that 68% of the data values will fall between one standard deviation above and one standard deviation below the mean. 95% of your data values will fall between two standard deviations above the mean and two standard deviations below the mean. And then 99.7%, guys. So that's pretty much all, right? Almost all of our data values will fall between three standard deviations above the mean and three standard deviations below the mean. So this is going to be important when we start looking at these distributions, these normal models, because we're going to be working and being asked to answer questions that have us think about if something is plausible as a normal model or something is unusual. So understanding the 68, 95, 99.7 rule will definitely help us with that. Okay, so that finishes up kind of the content from this chapter. I know we're getting into all the end of our first unit, and I continue to implore you to read the textbook. You know, this textbook is different. It's not like any other math textbook that you've ever read. I know you've listened to this video, about a 10-minute video, but nothing can actually be better than taking the 20, 30, 40 minutes to sit down and read the textbook. Look at the examples. Look at them working with these concepts. Okay, these are brand new things. All right, for the most part. So it's always helpful to get this content delivered in many ways. All right. So go ahead and watch this video, or I hope you enjoyed the video, and then don't forget to watch the video that starts to do some of these problems.